Okay, today we're going to start with hypothesis testing and confidence intervals. We'll be doing hypothesis tests and confidence intervals every day for the rest of the semester. It always follows the same general process. The math's going to be different. There are going to be some other things, but the process is going to be the same. So I'm going to start with kind of where we've been a little bit. We have this sampling distribution, in this case, X bar. We're going to have a center of that, and that's going to be some hypothesized value of the parameter. That's H, mu H, sorry. You'll see it sometimes in some books called mu 0. You'll see why that's the case in a minute. Well, anyway, we'll take three basic approaches to saying whether or not we think that's an appropriate conclusion. Let's say that we hypothesize that the mean is 20. One thing we might do is compute the sample mean and construct an interval around that mean, the mean plus or minus some margin of error. So we might get a confidence interval that goes from here to here. That entire interval is less than 20. Therefore, we're going to be able to conclude that the population mean is less than 20. Again, this interval is based on the center of X bar and then a margin of error on both sides. Although you usually see it with proportions, it's the same concept you see in the news and political polls and that kind of thing. So we'll construct the interval and look at the interval in relation to whatever hypothesis we have. If we had an interval that spanned from here to here, again, that's X bar with a margin of error. The population mean is in that interval. Therefore, what we will conclude is the population mean could be 20. We don't conclude that it is. It could be anywhere in there within our level of confidence, but it could be 20. We won't reject the idea that it's 20. Down here on the first one, we would reject the possibility of 20 because it's nowhere in the interval. Here we'll say it could be 20 because 20 is in the interval. So that's the first approach we'll take, called the confidence interval approach. We'll take our statistic and then compute a margin of error and then compare the interval to the hypotheses that we state. MOE, margin of error. Some books call it M, some call it E. I happen to be a Three Stooges fan, therefore it's MOE. So that's one approach, confidence interval. The two other approaches, critical value approach and p-value approach, are essentially the same. They're just sort of, I don't know if you want to call it inverted or mirror, but related for sure. So what we'll do then is we'll start with the critical value. I'll just call that CV, critical value approach. And what we'll say is that, again, let's say we have a mean hypothesized equal to 20. We might say we want to know if we can conclude that that population mean is greater than 20. So what we might say is that if we get a certain number of standard deviations above 20, we'll reject HO. So let's say that, and I'm actually selecting this number for a reason, it's one that we'll use, 1.645. If we get more than 1.645 standard errors above 20, we'll conclude that the population mean is greater than 20. So that'll look something like that. This is going to be called a null hypothesis. Don't worry too much about that right now. We'll get to it. But the statement's going to be something like this. Reject HO, which is the null hypothesis, if z-test is greater than 1.645. I'm just going to say this, but this could be, if we wanted to show the population mean was less than 20, then it might be over here, and we'd be trying to show that the mean is less than minus 1.645. Or in some instances, we might start off just saying, is it different? And then we'll say, is it greater than some value or less than some value? Now the value won't be 1.645 then. It'll be 1.96. But that's just a very broad overview of the critical value approach. Very much related to the critical value approach is the p-value approach. And it kind of goes like this. Let's say that again, mean is hypothesized as 20. And if we had z of 1.645, this area is going to be 0.05. That's called alpha, or level of significance. So when we compute the z-test again, we might get, let's say, 2.4 standard errors above the mean, and the p-value is going to be, since we're further out, it's going to be lower than 0.05. So now what we're doing is computing the probability of the statistic we observed if HO is true. You're going to hear me say that over and over again, and I know it's kind of a backwards logic in a way. But if we get a low p-value, the probability of getting the statistic that we observed is very low. We're going to say HO isn't true. On the other hand, if we compute a statistic, let's say X bar here, then the area in the tail is going to be greater than 0.05, and we're going to say that 20 for the mean could be true. So all three of these answer the same question, and if I match up the level of significance and the level of confidence, we'll have level of confidence here, and for the critical value and p-value approaches, level of significance. If I match those up, all three approaches are going to come to the same conclusion. Historically, the critical value approach is the approach that was used first. A lot of texts don't use it anymore. I still use it because I think students kind of understand it a little bit better, and then they get into a way of understanding the p-value. Because what this says is, when we get this many standard errors away from the mean, we reject HO. That's a little easier to start off with anyway, of saying that p-value. If HO is true, there's this probability of getting a statistic this far away. It's just a little harder to grasp at first. So I'll start with the critical value. Historically, and still used, is the p-value, the probability kind of thing. You can think of that as probability value. Now, the confidence interval is being used more and more. It's always been around, but it wasn't reported as much. But now we get a better, estimate of the size of the effect and what we really have. So we'll say here, for example, that we have 19.3 plus or minus 0.4. I'm making that number up. But we have just an estimate and then how far off we might be in general. Okay, the starting place in all of these just like it was with the central limit theorem problems or the sampling distribution problems, is to pull out the information from the problem. So there's some claim that the average population mean was 1,800. So our hypothesized mean is going to be 1,800. We think that it might be higher than that. I'm going to go ahead and put this down just because it's how you're going to want to read the problems. What we really want to know is the population mean, I shouldn't have written that there, is it greater than that 1,800? That's really what we want to know. Is the population mean greater than 1,800? We have a random sample of 40, and with sample mean of 1950 and a standard deviation, we're going to assume that the population standard deviation is 500. For this week, we're just going to assume values for the population standard deviation. Starting after the next exam, we'll see what happens when you have to compute the standard deviation from a sample. It'll follow the same process, but there are a couple of adjustments you have to make. Also, on the papers you guys have, that should be 90% for this problem. I've got it here, and then I wrote 95 down there. Okay, so I'm going to do two things here. First, the sampling distribution is going to look something like this. This is assuming that this is true. And we're going to have a standard error equal to the population standard deviation divided by the square root of n, or 500 divided by the square root of 40. I get that to be about 79.1, I'll call it. So now what we're going to do is make an interval around this 1950. And since this is 90%, if you're in the classroom now, I have those on the board. I will be giving you a handout and posting that on Blackboard that has that summarized as well. And this week, we're going to do everything with 95 and 90% confidence intervals, and we will only use levels of significance of 0.05. So the 1.645 and 1.96 both go with levels of significance equal to 0.05. But we want 90% confidence. That means we're going to go the mean plus or minus some number of standard errors, z sigma x bar. So we're going to have the sample mean, 1950, plus or minus the 1.645 times the 79.1. That comes out to be 19.9 to 2080.1. That is the 90% confidence interval. And now I'm going to draw this interval in relation to the sampling distribution. There's our 1800, but our interval starts at 1820, or 1819.9, starts here and goes up to 2080. The key point on that is the entire interval is greater than 1800. Therefore, we will conclude that the population mean is greater than 1800 because the entire interval is greater than 1800. While I have this up here, I'll get ahead just a second here. We're going to refer to this HO equal to 1800 as HO, or the null hypothesis. What we're trying to show, that mu greater than 1800, you'll see it called various things. HA is probably the most common. Sometimes you'll see H1, and sometimes you'll see HR. A stands for alternative. 1 is just 0, 1. R stands for research. What you're trying to show is what you put into this hypothesis. I'll probably call it either HR or HA most of the time, but you may see in books H1 as well. Null hypothesis means no difference. Therefore, it will always have an equal sign. Always. The null has an equal sign in it. You might see some books that would say less than or equal for reasons that you'll see in a minute. I just always call it equal. There's really nothing technically wrong with either one of those. But I find when we draw this sampling distribution here, that it's equal. That's what we do when we draw the sampling distribution. Some people will say less because if we conclude that it's greater than 1820, or I'm sorry, greater than 1800, well, it's also greater than 1700 or 1790. So that's why some would put that less than or equal. I guess you can make a case either way. Sometimes you just have to make a choice. My choice is equal to. Questions on confidence interval? Let me just say. When you work this problem, ultimately, a confidence interval problem, that's what you need to have. I think you can understand things, and we will, in one of the contexts or another part of the problem, definitely draw the sampling distribution. And you'll definitely want to have this, this information is just what you need to work it. And then for the p-value and critical value approaches, you'll need those hypotheses. Here. We've actually already done this part, draw the sampling distribution. And I should say the sampling distribution, assuming the null hypothesis is true. In a sense, what we're doing is setting a whole null hypothesis up. Well, one way to think of it is you're setting that up as a straw man, and your research is, it's not always exactly this, but you can think of it this way, trying to show that that's incorrect. I shouldn't say trying to see if it's incorrect. This is a scientific method. You shouldn't come up and say, well, what you're really trying to find is the truth. It either is or it isn't correct. But anyway, when we had the mean of that equal to 1800 and the standard error equal to, I can't remember what it was now, 79.1 about. That is the sampling distribution. Okay. Okay, so we're going to use the critical value approach. State both the null and alternative hypotheses, which we already did. HO is that the population mean is equal to 1,800, and HR, or HA, I'll call it here, mu greater than 1,800. Again, just kind of redrawing this a little bit here. We had our sampling distribution of X bar with a hypothesized mean of 1,800 and a standard error of 79.1. And so in the critical value approach, we're going to say how many standard errors above 1,800, how many standard errors above 1,800 will it take before we reject HO and conclude that HA is true. In this problem, we're using a level of significance, the letter alpha right here, of 0.05. And since we're only going in one direction with HA, that's called a one-tailed test. One-tailed upper, because we're only looking at some point up here. Well, for a one-tailed test, the Z value, as I've written on the board here and as you'll have in the handout, is 1.645. So that means we're going to reject HO if Z-test is greater than 1.645. And remember, Z is just the number of standard errors from the mean. So that's how we need to get, if we get more than 1.645 standard deviations above the hypothesized mean, we'll reject that as a possibility with an alpha level of significance chance of being wrong. Remember, in statistics, you can't be certain, you can be confident, you can state the amount of error that you're willing to accept. In this case, we're willing to accept being wrong 5% of the time. So our Z-test and you should think of this as something new because it's something we've already done, is the sample mean minus the hypothesized mean divided by the standard error. How far away from the center of the distribution is this value of X bar in standard error units? I'll put this on the graph in a minute, but I'll wait until I calculate this so I can put it on there a little bit more accurately. So X bar was $19.50 minus 1,800 divided by 79.1. That's about 1.90. So remember, we're going to cut off at 1.645. Since this is 1.9, that means that the value that we observed was, this is the X bar that we actually observed, is 1.9 standard errors above the mean. We said we would reject if we were more than 1.645 standard errors above the mean. We're 1.9 standard errors away from the mean. Therefore, we will reject HO, and we will conclude population mean put this back into the context of the claim is greater than 1,800. And then presumably make whatever decisions that we might need to make based on that conclusion. So since it's greater than 1,800 in this problem, what that probably means is customers are in for a rate change. An increase, of course. And if you're in charge of this business and you want to make money, you need to have a higher rate change because your payouts are more. Unless you want to go out of business. Let me go back and say, given this problem that I have here, stating the hypotheses is number one, state the null and alternative hypotheses, write a decision rule. This is the decision rule. Reject HO if the z-test is greater than 1.645. So that's part two. Show all calculations needed to generate the appropriate, that should say, test statistic. And the z-test is the test statistic. So that's part three. Just showing all the calculations. State your decision as to whether or not you should reject the null hypothesis. That's here, reject HO, that's step 4. State the conclusion the investigator is entitled to draw. The population mean claim is greater than 1,800. Okay, so for the p-value approach, first of all, well, I love it. Word and automatic numbering. Start with 2. Actually, we wouldn't do that, but we will for here. State the research and null hypothesis, or the null and alternative. We've already done that. I'll repeat it here. HO was mu equal to 1,800. HA was mu greater than 1,800. So we've already done that part. We're going to have a decision rule now, but it's not going to be the same one as with the critical value approach. With the p-value approach, it's always reject HO if p-value is less than some value. If the p-value is low, HO must go. So we're going to reject HO. This is our decision rule. If the p-value is less than 0.05. Show all the calculations needed to generate the appropriate, again, in this case, let's just say to generate the p-value. I was doing some cutting and pasting this morning. So I'll fix those things as I go along, and when I re-put this out or repost it, I'll have that on there. Well, I'm not going to re-show the whole thing here. We already know that the z-test that we calculated was 1.90. That was in the previous problem. Again, make sure you label the axes on these. That's still mu h. And the value that we observed, the x bar of 1950, what we know about that value is that z is equal to 1.90. the area in the curve here is the p-value. It's just what's left in the tail, in the direction of your alternative or research hypothesis. So this is what we've done before. In the z-table, we have 1.90, so that's 4713. Nothing new about that. So this is 0.4713, so the p-value is equal to 0.5 minus 0.4713, was it? I think I wrote 8, but that should be a 3. And that's 0.0287. So that is our p-value, 0.0287. And the p-value is less than 0.05, which means that we reject HO. So that's our decision. We're going to reject HO because the p-value is low. It's a lower probability of error than we're willing to accept. We're willing to accept 0.05, but this is a lower probability of error than we're willing to accept. And the conclusion will be exactly the same as it was in the other things. The population mean claim is greater than 1800. And obviously we knew the sample mean was greater than 1800. The sample mean is 1950. The question is it so far above that we would say it is definitely, or we're not definitely, we're confident that it's greater than 1800. And we can be, because the p-value is less than 0.05. Reject HO if the p-value is low. Okay, in the next problem, a company claims that their light bulb lasts an average of 1,000 hours with a population standard deviation of 80. We have 64 bulbs in a sample, and the average for those is 970. We already have said that the population standard deviation, we'll just have to assume for now, again next week we'll go beyond that, is 80. And we want to know if the average, the population mean, is less than 1,000. So our alternative hypothesis is that the mean is less than 1,000, and our null hypothesis always equal. It doesn't make any difference which order you write those in. I usually write the alternative or research first because that's what's in the problem. And we conclude that the average or population mean is less than 1,000. So the confidence interval is the statistic, X bar. I'm saying that way because that's going to hold all through. The confidence interval is equal to the statistic. Now it's X bar, but it could be P hat, could be X bar A minus X bar B, could be R. It's always, though, going to be the statistic. For now, X bar. Plus or minus a confidence coefficient, which is Z. Next week we'll do somewhere it's not Z, it's going to be T. Times the standard error. I'm going to write it sort of shorthand. Statistic plus or minus confidence coefficient times standard error. This is the formula we're going to be using this week, but this general formula will be on everything, I think, on exam 3 as well. We'll follow that general thing. We're going to do confidence intervals there. And some on exam 4 as well. 970 plus or minus, and for 90% it's 1.645 times the standard error. And the standard error is sigma population standard deviation divided by the square root of n, which is 80 divided by the square root of 64, which is 10. And that goes from 953.6, I'm going to round that, to 986.4. By the way, this part here, that's 1.645 times 10, or 1645, that is the margin of error. Another way to think about that is statistic plus or minus margin of error, and that confidence coefficient times standard error is the margin of error. That entire interval is less than 1,000. So if we're using this interval to test this specific hypothesis, we would conclude that the population mean life of the light bulbs is less than 1,000. One feature of confidence intervals, which is why it's sort of becoming the more used method for looking at these, is that you're not stuck with these hypotheses. You can also say from this that the population mean life is greater than 950 because the entire interval is greater than 950. However, you cannot say that the population mean is greater than 955 because 955 is in the interval and it could be the real population mean. It's as if this whole range is one number. Just think of it as one block number. We can say that it's less than 1,000. We can say that the population mean is less than 990. We cannot say that the population mean is less than 980 because 980 is part of this number, part of the interval. While we're at this right here, I'd like to show you how to get check figures on your calculator for this problem. So if you would take your TI calculator, think about now all the money you spent for this thing. Finally, this is going to be better than just a basic calculator. So if you would hit Stat and arrow over to Tests, then arrow down to option 7, Z interval. We're using the Z for an interval, option 7, and hit enter. You're going to input either data or statistics. Data means that we could put numbers in list 1 or list 2 and compute the whole confidence interval. In fact, it would compute the mean, the standard deviation, and the entire interval for those set of numbers that you had in, say, list 1. But we have the statistics already given to us in this case. We know, just arrow down there, that the population standard deviation is 80. We know that our sample mean is 970. We know that our sample size is 64. We know that our confidence level is 90. So you can either put 0.9 or you can put 90, and then arrow on to calculate and hit enter. And you should see the numbers 953, well, about 0.6, the same thing we calculated before, and the 986.4. So that gives you the lower and upper bounds of the confidence interval. So for the sampling distribution, awesome. The hypothesized mean was 1,000. The standard error was it 1645, I think? What was it? It was, no, it was just 10. I was giving the whole margin of error there. That is the sampling distribution. When we get to the other parts of the problem, I'm going to redraw it, but just to compare where we were at. While I'm on this part, I'm going to go ahead and just draw on here the confidence interval from the last part. Our confidence interval was 953 or 954 about to about 986. That entire interval is lower than 1,000. Therefore, we can conclude that the population mean lifetime of the bulb is less than 1,000. That's just a picture of it. Okay, so for the critical value approach, we're going to have, I'll write it this way now, HO was mu equal to 1,000, HR, we wanted to know if we could show that it was less than 1,000. So that's one, state the research and alternative hypotheses. The decision rule is reject HO if z-test, and here's where it's slightly different from the problem that we just worked. I'm going to go ahead and draw the sampling distribution again. We're going to reject HO when we get too low. So our Z value is going to be a negative value, and we're going to reject HO when it's lower than that. So this will be less than minus 1.645. So if we're trying to show it's less than minus. And the other problem we were trying to show was greater than. If it was greater than a positive number of standard deviations away. The z-test on part 3 is equal to the sample statistic, x bar, minus the hypothesized mean, divided by the standard error. It's just a little hop, skip, and a jump from what we've been doing. Actually, not even that much. How far is the value we observed from the center of the distribution in terms of standard error units? Z is the number of standard deviations or standard errors from the mean. So we have 970 minus 1,000 divided by 10 is equal to minus 3. So the 970 is 3 standard errors below the mean. minus 3 is less than minus 1.645. Therefore, we are going to reject HO and conclude, this was part 4 and this is part 5, the population mean life of the bulbs or the light bulbs is less than 1,000. In other words, they've made a false claim. They said it was 1,000, and you can now show that it was less than the length of time that was claimed. Okay, again, that's just what we had from the previous problem, the sampling distribution, the hypotheses, and we had already computed z-test to equal 3. So this is part 1. Part 2, write a decision rule in terms of the p-value. We're going to reject HO if the p-value is less than 0.05. There are no negatives or anything like that. These are probabilities. Reject when the probability is low. So it's less than minus in the critical value, because you could be standard deviations on either side, but the p-value is always reject HO if the p-value is low. Low means lower than the level of significance that you have in the problem. So for part 3, we're going to compute the p-value where we already have the z-test. So we know we're z equals 3 standard deviations. That's minus 3 actually. But we can look up 3 then in our z-table. Well, and that's 4987. So from here to here, from our hypothesized 1,000 to the 970, 3 standard deviations, that's 4987. So that means that the p-value is equal to 0.0013. That's just 0.5 minus 0.4987. So that's the rest of the calculation. Our decision, we said we would reject if HO was less than 0.05. Our p-value is less than 0.0013. So we reject HO. I'm sorry, the p-value is equal to 0.0013, which is less than 0.05. Therefore, we reject the null hypothesis. Conclude. And this is going to be the same thing in every part. As long as I match up the level of significance and the confidence level, then it's always going to be the same decision. And when I get problems, I will endeavor to do that. A lot of textbooks mix that up in the middle of the problem and all of that. I personally don't find that useful. Conclude, the population mean life of the light bulbs is less than 1,000. Again, we don't need any hypothesis test to say that the sample mean is less than 1,000, but we're trying to use that sample information, the X-bar of 970, and our knowledge of sampling distributions, how spread out things are, to also go beyond the sample to say something about the larger population. That goes back to about the first day of the class. Larger population, it has parameters like mu and sigma. We're really interested in the mu. We get a sample, we compute X bar, and we use that sample information to estimate or test a hypothesis about the mean of the larger population. If you look at the very beginning of the OLI, the online text, it has a fantastic picture of this. And just looking at that picture, I think is pretty cool. I'm not that good of an artist, so this is what we're going to get here. Okay, in the next problem, the aptitude test required has a mean of 500 and standard deviation of 120. We have a random sample. I'm going to go ahead and write that standard deviation down of 120. And a random sample of 36. We have a sample mean of 546. And we want to know if we can conclude that the mean score, the population mean score, is different from what's expected. So HR is going to be mu different from 500. Notice in this case, we didn't specify ahead of time that it was going to be greater than 500 or that it was going to be less than 100. When you really do scientific method, you formulate the hypothesis before you collect data. So even though we know that the score was, now we know it's 546, your hypothesis should be stated before you have that knowledge. And then HO will be mu equal to 500. Really don't need that part for the confidence interval, but while I have the whole problem here, I want to get that up there for the next parts. Okay. So for the confidence interval, we're going to have the statistic plus or minus margin of error, where margin of error is equal to the confidence coefficient Z times the standard error X bar. And our sigma X bar is equal to sigma divided by the square root of n. Remember, that's just the central limit theorem stuff. And that's equal to 120 divided by the square root of 36, which is 20. As an aside, if we weren't sure that the population was normal, with an n of 36, we would have to know that we don't have outliers or extreme values in order for this analysis to be in line with the sample size requirements to have a bell-shaped sampling distribution. And sometimes I'll ask that in the context of one of these problems. Is the sample size large enough? Or under what conditions is it large enough or too small for that matter? Not large enough if you have outliers or extreme values. Skew's okay, and of course if the population is normal, you're okay. It's just an aside. Sample mean 546 plus or minus for a 95% confidence interval is 1.96. Now think about this. The empirical rule, 95% plus or minus 2 standard errors, approximately. Well, 1.96, exactly. That's about 2 standard deviations. So this 1.96 ought to make sense in terms of all the way back to the empirical rule, plus or minus about 2 standard deviations, or standard errors in this case, times 20. And that's 506.8. to 585.2. So if we're trying to show whether or not the population mean is not equal to 500, we can say that we're confident at the 95% level that the population mean is not equal to 500 because 500 is nowhere in the interval. Okay, in this case, this is going to be a two-tailed test because that's not equal to. When we had the problem, it just said, can we see if there's a difference? We didn't imply ahead of time a greater than or a less than. That means we would reject HO if we found a value that was too low or if we found a value that was too high. So the decision rule and the rejection region is on both sides. So when we do our decision rule, it's going to be reject HO if z-test is greater than some value or less than minus that same value. And for a two-tailed test for the z-test, that value is 1.96. So in other words, about 2. If we get more than about 2 standard errors on either side, we will reject the null hypothesis. Z-test calculation, exactly the same. X bar minus the population mean over the standard error. So the X bar that we had was 546. 546 minus 500 divided by 20. I think that's going to be 2.3. And it is. 2.3 is greater than 1.96. We're going to reject HO. And we are going to conclude that the population mean for, it says this group. So the population mean for this group of applicants is greater than 500, greater than that value in the population. Which I think would lead you to think maybe this is a pool of applicants you would like to consider for the future. They tend to get higher scores than the average, and we're confident about that. Okay, so here's the kicker for the two-tailed test. The p-value is not just the 0.0107 that we have over here. It's a two-tailed test, so we have the same amount of p-value over here. So the total p-value is going to equal 0.107 times 2, or, 0107, or 0.0214. That is less than 0.05. And so we're going to reject HO, have the same conclusion that we had before, that for this pool of applicants, the population mean is not equal to 500, not equal to. We're not going to say greater than, we're going to state this in terms of the hypothesis that we had before we collected any data. I'm going to say one more thing, and we'll have more to say about confidence intervals and p-values and that tomorrow, and a couple of other concepts. But here's an example of a two-tailed test that might get you into that idea of state the hypothesis, and then it could be positive or minus. And the example I'll give you is that when I was working for Tyson Furniture Company back in the early 1970s, actually, it was Dyson, not Tyson. It's not a chicken company. Dyson in North Little Rock. We had a break room, and in that break room, we had this Coke machine. And what would happen is you put your 10 cents in, and a 6-ounce cup would drop down. Then the machine would put some ice in there, and then some Coke would come in. Well, so you had that cup. And let's say you wanted to have 6 ounces in there. Well, what you want to know is, when do I need to make an adjustment to that Coke machine? It could be that up here means that we're spilling Coke out, wasting it, if it got too high. If you're putting too much in there, then you want to fix the machine, readjust so it's putting in the appropriate amount of cola. On the other hand, it could be off on this side. That is, it's not putting enough in there, it fills it up halfway, or not at the level that I and my colleagues would expect, and we would be complaining because our Coke wasn't full. So this test isn't just performed once, it's a quality control test. It's going to be performed more than once, and what we want to know is, when is what we observe, when does our statistic tell us that we're out of control? And it could be in either direction. So when we get, in terms of the critical value, more than about 2, 1.96 standard errors away, we'll readjust. If not, we'll consider this normal operation. Of course, if normal means it's under or overfilling anyway, maybe you need a cup that's a little bit too big, and you hopefully, and set the standard such, have a machine that doesn't have a lot of variability in it. That's the whole idea of quality management and that kind of thing.